In the case 1, fitting a straight line. So given a function f of x is equal to a plus bx, so we know that this one is a function, it's a linear function, meaning you can represent any line. For example, you have this line, or this line, or this line, a straight line. You can represent that one with any value of a. Okay, f of x equal to a plus bx. So by simply changing the value of your a and b, so you can represent this line. Okay, and whatever straight line you can form, except there's only one exception. If you have a straight line that is I think x, no, I think there's no exception in this. Okay, so meaning if you have a set of point, for example, you have a set of point here, okay, and then you can represent those points with a straight line, and the function of a straight line. Okay, so fitting a straight line to data is also known as linear regression. So recall the minimization function S. Okay, in this case we only have two coefficients, a and b, because here you can see a and b. Okay, now b or a is the y-intercept, and while b is the slope of the line. So you can see the physical meaning of this linear function. Okay, so our goal is to minimize S, and for sure we know because this is a square, okay, it's a least square, so meaning the minimum value of S should be equal to 0. Okay, so we would like to make the function of x, or the line, this one is the line, okay, and then this one is the data y. Okay, so given x, then we have the y. So what is the difference between those things? Okay, meaning if you have a line here, if you have a set of points, let's say you have points here, this one, okay, and then you want to represent that one with the line. Okay, so that's a straight line, I hope. And so meaning every point there should be a difference. So what will be the difference? This one is a function of x, right? And then now the difference is you have y here, y1, okay, with respect to y. So if there's a y here, so x, and you have y. So if you have that point, there's a y1 there, then you have y2, y3, y4, and y5. Actually, we can partner that one with the respective coefficient, okay, respective x in that case. So with respect to x, we have x1, y1, okay, then we have x2, y2, x3, y3, okay, x4, y4, then x5, y5. Okay, now given the function of x, so meaning this is our, let's say this is the best curve, okay, this line. Here the difference between y1 and then the function of x, which is the line, when you input 1, okay, and then the other one, y2, subtracted by the function, the line, where when x2, at x2 here, what will be the value of your f of x? So that is your f of x, x2, okay. So meaning you have this one. So we know, let's say this one is 0, this one is, we don't know, but there's a difference. And then also if we in y3, we have f of x3, okay, a certain value here, and you can see here this is the f of x3. Okay, so given the x3 here, so this is the corresponding point. Okay, and then so on and so forth for y4, y4 minus f of x4, then y5 minus f of x5. Okay, and taking the square of these things, okay, whatever the value here, and then you simply add all of them. Okay, our goal is to minimize the difference between them such that compared to this line here, if we construct another line here, let's say the line is like this, you will see a huge difference between compared okay, so let's say this is g of x, and we know that if we replace this one with g of x, okay, we replace this one with g of x, function of g. Okay, so you will see a huge difference, for example here versus this point here. Okay, so you will see a huge difference. Then also here and this point here, a very huge difference. So meaning our value here will be larger compared to the function of f. Okay, so function of f is better than the function of g. So that's our goal. So we have here with the partial derivatives with respect to the two coefficients and equating them to 0 to obtain the optimal values of these two coefficients. So we have here, okay, the function here, take the partial derivative in terms of a, and the other one is with respect to b. Then equate them to 0 because we know that if we equate the first order differential equation to 0, we get the maxima and minima. In this case, we get the maxima. Okay, so having these equations, divided both sides by both equations by 2 times n plus 1, so we will derive these equations. Okay, 2 sets of equations. Then by simply arranging them, we will get this one. So for example here, okay, so you will get this, okay, this value here, and then the y also, okay, which are the mean values of x and y data. So we know, this one is the mean value. X with the bar is the mean value, so simply the average of all x, and then y bar is the mean value of all y. Okay, so this is not part here. Okay, so now therefore by simply using this one here, the above equations, you can derive the coefficients a and b, okay, respectively. Now these both equations, okay, because our goal is to find the coefficients such that we can construct the function that can fit a straight the data points, no, a linear function that can fit the data points. So we need a and b, but these two functions here are both susceptible to round of errors because of so many math operations, multiplication, divisions. Okay, you have the power, so round of errors is a bit challenging for a and b. So therefore, by reformulating the parameters, for example this one, we can get the a, okay, by simply arranging this one, and then also by using the mean values applied to this one here. Okay, for example, you replace x bar with this one here, and also by putting the elements or the values here outside, and you will get here distributive property. Okay, so we have a simpler equation for b and a. Okay, so that's it. So that's the idea of the linear regression, or fitting a straight line, or fitting the data points with a straight line. Okay, the function a plus b. So this is the very simple illustration of the least square curve fitting.